Researchers from the University of Delhi and the Raman Research Institute, or RRI Bangalore, may have stumbled upon one of the most massive exoplanet revolving around the binary star system, X-ray binary MXP 1658-298. The Research Matters team caught up with Professor Biswajeet Paul, one of the scientists responsible for this discovery. Professor Paul is a professor at the Astronomy and Astrophysics group at RRI. He has been studying the evolution of binary star systems, a system of stars consisting of two stars orbiting around each other, unlike our solar system that has just one star, the Sun. Specifically, Professor Paul's interests lie in binary star systems where one of them is a compact object like a neutron star.
For several years, I have been interested in the study of X-ray binaries, in particular evolution of X-ray binaries. For various reasons. One is single star evolution is different from evolution of stars when they're in a binary system. One star impacts the other in various ways. And so there are a lot of statistical processes that can be understood by, first of all, measuring the evolution of orbits of X-ray binaries, and there are different techniques for it. What applies to a system when you have a pulsar, that is a rotating neutron star going around a companion, is different from when you do not have such a clock. If the companion is not a pulsar, then you apply different methods. So we have been investigating various sources for their orbital evolution, and this is one of those. And this source actually one Dr. Chetna Jain from Delhi University, who did much of her PhD work with me, studying orbital evolution of other sources. And this is a source on which we had started work several years ago, almost 7-8 years ago. We did some preliminary work. Part of that was published in conference proceedings, but the data didn't make very good sense to us then. It's only recently, when we had more observations, all of it fell in place and we could make sense of it.
The two stars of MXP 1658-298 are aligned such that when the companion star passes in front of the X-ray emitting neutron star, it causes an X-ray eclipse. Now, if we know the time between the two eclipses, we could, with some accuracy, predict how the binary system evolves. While looking at these eclipse periods, Professor Paul and his team found discrepancies in the data that could only be explained if there was a third body orbiting the two stars, leading them to propose the presence of a massive circumbinary planet.
In this particular case, what we do is that the neutron star is not a pulsar in this case, so we do not have a clock going around the companion. What we therefore use in this case is X-ray eclipses. So this is a low mass X-ray binary, which means you have a neutron star with a very low mass companion. We don't know the mass of the companion as yet very accurately, but it's low mass star, let's say less than 1 solar mass. As they are going around the common center of mass, for a narrow solid angle in the around the orbital plane of this system, if there is an observer, the observer will find the X-ray star to be eclipsed by the companion once every orbit. So it is the eclipse which helps us keep track of the evolution of the binary, if any. Advantage of this is here the companion is a low mass star, so it has very little stellar wind. Okay, and the X-ray emitting object is very small in size, only about 10 kilometers, and going around at a speed of several hundred kilometers per second. So it goes behind the companion very quickly and comes out of the companion, from behind the companion very quickly. So the eclipse transitions are very sharp, and when you have very sharp transitions, you can measure the middle of those two transitions accurately, which means for such a system which has an orbital period of about 20,000 seconds, we can measure, if you have a good observation, every time we can measure the mid eclipse time with an accuracy of better than a second, of the order of a second. Okay. That's what helps us to keep track of the orbital period of the system. If there is slight change from the orbital period, you would expect the next eclipse to come a bit earlier or a bit later, and that's what we are after. So we continue doing that, and that method has been successful in several other sources, finding some other interesting things. For example, in one source we found a sudden glitch in the orbital period. Okay. In this case, we are just keeping track, and then for a period of about 2 years, during 1990 to 2001, there are many observations of this source, we found that a simple deviation from a straight line wasn't enough to describe the data. Instead, we found some oscillations with a period of about 2 years. Oscillations in the changes in the time of the eclipse compared to what you would expect. If the change was in one direction, that is, eclipses are coming earlier and earlier, you could interpret that the orbit is decaying, the orbital period is decreasing. If the eclipse is coming a little later, you know that the orbit is evolving. And then you go into details of why this orbit is evolving. Is it because of mass transfer, or is it because of mass loss from the system? Is it because of tidal interaction between the two? Those are the things we are after. In this case, what we found is with about 25 eclipse measurements over a 2-year period, we found that the eclipse is not only advancing and not only it's kind of oscillating around an expected value, and that will happen if the binary itself is moving around. And what may cause the binary to move around? If there is a third body, and that's our interpretation. And from the available data, basically the time scale for that oscillation, and if you have that oscillation, how much is this system moving, the amplitude of that arrival time delay of the eclipse, which is turns out to be about 10 seconds. So these two together, and an assumption for the mass of the X-ray binary system about 2 solar mass, which is a very reasonable assumption, we get a mass in the range of about 21 to 26 Jupiter masses for the third body, which would be one of the most massive exoplanets.
A circumbinary planet, unlike the planets in our solar system, behaves very differently. Since it orbits two stars, it interacts with both of them through gravity.
I should make it clear first, I am not an expert on exoplanets at all. That's not my area of research. Here, while looking at the exoplanet, we just happen to find one. But if you have a third body like that, the third body does a lot to the inner binary. You can imagine, compare it something like the Earth-Moon system. Moon is the third body in this case, and the Earth itself you can consider as Earth and its liquid surface. Okay. Moon causes tide on Earth, so something similar would happen with the third body around an exobinary. These two binary systems are bound gravitationally, but not of a fixed separation. Right? So if the presence of the third object we choose would exert something like a tidal effect onto the inner binary system, and there will be exchange of angular momentum. For example, in Earth-Moon system, Earth is spinning at a rate of once every 24 hours. Moon is going around in 29 days. So as a result of this interaction, Earth loses angular momentum, Earth is slowing down, and Moon gains angular momentum, Moon is going farther away. Same thing would happen in an exobinary like this. The third body, which is going around the exobinary, let us say, over about 2 years standard time scale, whereas the binary is going around each other at 7 hours. Okay. The effect of this is the outer body will gain angular momentum and would go further away. The inner one would lose angular momentum and come closer. So that may be the reason why the orbit of this binary is also decaying. Okay. At a rate of several million years time scale, the inner binary is shrinking. There are other exobinaries known where the binary system is shrinking, but what causes that shrink is not very clear. So this what might indicate that maybe they have a third body too, not found yet.
Finding planets around stars other than our Sun can be quite a challenge. It becomes all the more difficult if the stars they belong to aren't always bright or there isn't adequate data available to make any predictions.
Starting an exobinary evolution in this manner is actually not complicated. All that you have is an X-ray light curve, which is a plot of intensity as a function of time, and you see eclipses. And that is very similar to how, for example, an exoplanet causes eclipse on a otherwise visible star. The planet comes in front and the light falls down. And here it's somewhat different, that you are looking at the X-rays coming from the central object whose intensity falls. That time marker, that's middle of the eclipse, is a kind of useful tool for us to keep track of the location of the binary. Okay. So technique-wise, it's not very complicated. What makes it difficult to pursue this particular system? So there are two issues here. One is all these observations have to be done from space, because we are doing all these detections using X-rays only, and X-rays do not reach us because atmosphere absorbs them, unfortunately. So you need to have instrument in space. Okay, which of course there are limited opportunities. We now have AstroSat, and most of these studies are done with observatories flown by NASA and ESA and so on. So one needs to get observation time or use archival data. So resources are limited for you to make these observations. That is one side of the difficulty. That there are only few space observatories at a time, and there are a whole range of different programs for different people to pursue. The field is very complicated. To get an observation time or the amount of archival data that is available is also limited. Another complication for this particular system that this is not a persistent system. The source is not bright all the time. It was in and outburst during 76 to 78, went into an outburst again during 1999 to 2001, and is currently at the end of an outburst, which also lasted for about 2 years or so.
Although an accidental discovery, Professor Paul and team are very excited about it and now intend to take a closer look at the star system MXB 1658-298.
This particularly, the detection itself was quite exciting, that we are not looking for such a thing. Our study was on evolution of the binary system. Having found it, we realized that this is a very unique system. The circumbinary planet that we have found turns out to be the most massive planet ever found around any circumbinary system. Okay, so whenever you are studying a process, if you found some extreme examples of that, that often helps you constrain the processes involved. Okay, we are not exoplanetary scientists, but I'm sure people who work on formation of planets around binary systems will find this discovery useful in their models. That's one thing. Second thing is, as I said earlier also, when you have a triple system, okay, the less massive object, if it's in a larger orbit, it would exchange angular momentum with any one and would drift away. Okay. So for this system, then we can try to investigate where this system was in the past. Okay. So migration of the planet around binary stellar systems is another very important topic. And in this system, the planet has already migrated away to quite large distance, about 1.5 AU, that is the Sun-Earth distance. Okay. So one can probably trace it back to where this object was. Okay. So this is important both from the point of view of migration of planets away from binary systems and very massive planets. None of which are, this system provides you two extremes of this kind of study. So this has some impact in the wider study of circumbinary planets as well. While there are about, I don't know the number exactly, more than 2000 extrasolar planets are known, maybe even more. Circumbinary planets, I think there are about 20 known. Among them, this is one of the most extreme systems. It is the most massive one, it is at a large distance, and it is around a low mass extrabinary system. Low mass extrabinaries having a neutron star of low magnetic field strength are also very old systems, which means that this object is very, very old. So having a planet around a very old system would help you constrain the studies of migration of planets around binary stellar systems.